Hi. Today I will introduce my new paper, CanonicalFusion, generating drivable 3D human avatars from multiple images. We approach the question of how to accurately reconstruct a person in 3D when given a video or image of them, and how to make them move as I desire, like walk in a zigzag pattern forward. From the perspective of 3D human reconstruction task, creating an animatable avatar requires implementing a realistic canonical model. To solve this task, various research has been conducted to predict realistic mesh in canonical space and its skinning weights for further animating. Some methods take multiple post-scan models as input, while others use dense multi-view frames as input to predict the canonical model and pose-dependent skinning weights. However, these methods often require a large number of images or skin meshes as input, which results in significant training time for canonicalization and creates a challenging training setup. To reconstruct the canonical mesh in monocular video setting, which is easy to capture, we propose a method called CanonicalFusion, which reconstructs a realistic canonical avatar from single-view multiple frames, video or image, using an explicit approach. Here, we propose forward skinning-based differentiable rendering to integrate information from sequential images and refine the canonical mesh. Our method can update the geometry with just 3 or 4 frames, and the process of creating a canonical mesh from the data for one avatar takes only about 13 minutes. By attaching a text-based motion generation module to this canonical avatar, it is also possible to animate the avatar, as shown in the figure. The following is an overview of our pipeline in detail. Our motivation starts from predicting LBS directly on reconstruction. By taking input image and its corresponding fitted SMPLX depth map, we jointly predict LBS and depth map as an explicit way, so we can directly canonicalize the predicted mesh from given image by using the estimated LBS map. Here, the LBS map is compressed into a 3D value through an MLP, multi-layer perceptron, instead of the usual 55 dimensions, and this compressed LBS map is decoded back into 55 dimensions through an MLP decoder. Using this method, we can canonicalize the posed mesh obtained from the depth map with the predicted LBS. Additionally, the color map is simply predicted based on the normal map derived from the input image and the predicted depth. The resulting canonical mesh can then be updated by integrating information from other images through our proposed forward skinning-based differentiable rendering. This process results in the final refined canonical mesh as the output of our pipeline. First, we do compact parametrization of skinning weight map to represent 55-dimensional map to 3-dimensional map. We augment those weights by doing barycentric interpolation on SMPLX UV map and use them as the training dataset for compact parameterization of LBS. We use simple autoencoder MLP network to encode and decode it back to full 55 dimension. We use L1, KL divergence and non-zero loss. The UV map is the result of compact parametrization of LBS map after the MLP encoder, which is visualized on the SMPLX UV map. This is the result of encoded LBS mapped visualized on UV map and SMPLX mesh. The right one is the deformed mesh using decoded LBS. We can see that the MLP network works well since there is no artifact on deformed mesh. Then we use this compressed LBS map and depth map as GT and predict them using input image and fitted SMPLX depth map. We use simple attention UNet with separate LBS and depth map decoder branch. We use some common losses like L2 and SIM loss to train this network. After predicting the depth and LBS maps, we also aim to predict the front and back color maps. For the front color map, we use a ground truth color map where lighting effects were removed, so the network could predict a map without lighting influences. To further improve the performance of the color map prediction, such as predicting the details like wrinkles, we convert the depth map obtained from the joint depth and LBS prediction network into normals, and used this normal information along with the input color map to predict the color map. For the loss function, we use a combination of L2 loss and perceptual loss, specifically VGG loss. Note that after training the joint depth and LBS network, we freeze its weights and then train the texture network. Since we now have depth and LBS map of the input image, we can directly canonicalize the posed mesh reconstructed from depth map. However, this inverse skinning process fails to recover unseen geometry, such as armpit or arm, where the reconstructed mesh is not separated or occluded. Therefore, if we remove the faces stretched above the predefined value, these regions remain empty in the canonical space. To fill these empty regions, we combine the canonicalized mesh and canonical template mesh through signed distance integration. We take the signed distance of the canonicalized mesh if there exists canonical vertices v_c near the xc. We empirically set tau to 5 since this value is proper to integrate those meshes. The posed mesh reconstructed from the image, as shown on the left, can be directly canonicalized using the predicted LBS values without needing an additional SMPL fitting process. The center image shows the avatar that was directly canonicalized. When we integrate this mesh with SMPL in the SDF space with this process, we can get the result shown on the right. This mesh retains more detailed information about the hair and clothing compared to SMPL, which allows for more natural results during next differentiable rendering process. Once the mesh is canonicalized, we need to integrate the geometric and texture information from multiple frames. Since the canonical space retains the same information regardless of the pose, we refine our initial canonical mesh using forward skinning to integrate pose invariant information from the posed frames. We use a differentiable rendering approach that updates the 3D mesh explicitly by utilizing normal and mask images. Here, we apply forward skinning, which is fully differentiable, to account for the various postures in each frame. First, we render the normal and mask images from the posed meshes reconstructed from each frame. Then, we update the geometry of the initial canonical mesh. Here, we select a reference frame with the smallest chamfer distance with the canonical SMPLX mesh for multiple input images and used the reference frame as an initial canonical mesh. Since there can be pose inconsistencies or errors in the SMPL fitting, we also update the initial human pose parameters to account for these pose errors. This step is critical because our differentiable rendering process involves forward skinning, which depends on the poses from each frame. We achieve this by calculating the chamfer loss between the estimated posed mesh and the deformed initial mesh based on the pose. After updating the geometry, we also optimize the color using L2 loss with the texture map estimated by our main network in the previous step. We evaluate our main network's performance, which reconstructs posed mesh for each frame with other works like PIFUD, Icon, and Econ. Our results perform better than previous image-based reconstruction methods both in front and back side. In this table, ours perform best on all the test sets, including RP, 2K2K, TH dataset. For testing, we select 20 scan models from each RP and TH 3.0 dataset that were not used for training. We compare the R proposed forward skinning based canonical mesh optimization with the SCA NIMIT, which takes a set of raw scans to generate a canonical mesh. SCA NIMIT relies on the SMPL model to canonicalize the raw scans and to fill missing regions, therefore, it fails when there are pose errors. To compare SCA NIMIT with our method, we take the same input as SCA NIMIT, which is multiple raw scans, and use the same SMPL body pose parameters and run our forward skinning based canonical mesh optimization. When you look at the performance comparison based on the number of skin meshes used as input, whether it's 5 views or 15 views, our method consistently produces more natural canonical meshes and smoother reposing results. Here, we've included one of the ablation results, which verifies the proposed pose error update in the differentiable rendering section where we update the geometry. In this example, we intentionally added pose noise to the arm of the initial canonical mesh created from the input frame. When we perform differentiable rendering on this dataset, if the pose update loss does not exist, you can see that artifacts appear on the arm during the update process. We also conduct additional experiments on various datasets. The image on the left shows the results based on the Actors HQ dataset, which captures real people moving frame by frame with realistic clothing deformation. As you can see, the canonical mesh generated is quite natural. The image on the right shows the in the wild results, where my lab colleague captured me performing various movements while wearing loose clothing captured by iPhone, and reconstructed the canonical mesh. It demonstrates that the method can handle loose clothing to a certain extent. Additionally, we utilize the SMPL template model to replace the hands with SMPL's hands in the SDF space, since updating the hands through differentiable rendering can be challenging. For the texture, we sample the color from the face, particularly the nose area, and apply it to the model. This canonical model can be animated to perform arbitrary motions using text-based motion generation models like T2M-GPT. For example, in the following result, we use the canonical mesh to create a video where it performs a jumping in place motion. This result is also an in the wild example, and he is one of my lab colleague. In this case, we can also apply a text-based motion generation model to simulate a golf swing. The video is captured in an environment with significant illumination effects, but as you can see, the texture network was able to remove lighting influence to some extent, resulting in a more natural mesh. Thank you for attention. This is the QR code link for our GitHub page. Please visit our page for further question.